So in this video, we're going to talk about the limit comparison test. Comparison test. Before we talk about the limit comparison test, let's review the comparison test with sum of n equals to 1 to infinity of 1 over n squared plus 1. And so this one should be fairly obvious that we know that n squared plus 1 is most definitely greater than, which means 1 over n squared plus 1 is less than 1 over n squared, which means this is less than the sum from n equals 1 to infinity of 1 over n squared. And since we know this converges, we also know that this will converge, because this is a larger series, and if the larger series converges, then the smaller series must also sum to some finite number. And so then alternatively, let's think about what happens instead as n goes to. We have the same series, but now instead of n squared plus 1, we have n squared minus 1. And we want to know whether this series converges or not. So intuitively, as n gets very big, whether it's plus 1 or minus 1, it really shouldn't affect our end behavior or our sequence behavior too much. However, we can now, this comparison is no longer valid because n squared minus 1 is less than n squared. So 1 over n squared minus 1 is now greater than 1 over n squared. So this is no longer, we can no longer make this comparison. And if we were to make the opposite comparison, so if we say that this is greater than our known converging series, then this becomes what I call a meaningless comparison, because you know this converges, but this is a number bigger than your converging series, so we really don't know what's going on. But intuitively, we feel like, well, when you're going to infinity, subtracting 1 from infinity squared isn't really going to change too much about the behavior of your numbers. And so somebody took this intuition and decided, well, why don't we compare, oh, I had extra space. Why don't we compare the behavior of two series? And so what the limit comparison test says is, which I'm now going to shorthand form to LCT. What the LCT says is, so let's call our sum AN, and we want to compare it to BN, the sum of BN. How we compare this is, now instead of comparing with greater than or less than, we're going to say, well, if AN converges if BN converges and AN is some multiple or some factor of BN, then AN will also converge. So BN converges, AN is some factor or multiple of BN, AN will also converge. Alternatively, if BN increases unbounded and AN is some factor or multiple of BN, then AN will also diverge. So how do we find if AN is a factor of BN? Well, we divide, really. So we divide AN over BN, alternatively BN over AN, because then you'll just get the reciprocal. And we could divide term by term, but really all we particularly care about is the end behavior. And so instead of comparing all the terms, let's just compare our largest term. And our largest term is when n goes to infinity, because we're counting to infinity. And so from here we have, in this particular case, let's take our an to be 1 over n squared minus 1. And let's take our bn to be 1 over n squared. And so we get 1 over n squared, the limit n goes to infinity, as n goes to infinity of n squared over n squared minus 1. And we know this is equal to 1, which means that at some very large term, an is a multiple of 1 of bn. Yes. And so we can say that an has what we call the same behavior as bn. Since we know bn converges, so since we know this converges, so we also know that this will also converge. Yes, this is very poor notation, but to make the point of saying, well, if we know bn converges, then an will also converge. And this will work, so we can say that these two will have similar behavior if the ratio of an to bn as n goes to infinity is any number between and not including 0 and infinity. So any real number, really, because then what we're saying is that an is a factor or a multiple of bn. And the reason 0 and infinity don't work is because if you have a finite number divided by an unbounded infinite number, then you'll produce 0, right? For example, if you have 1 over infinity, limit as n goes to 0, this will produce 0. Well, this was a poor example. Yes, this is a poor example because of the harmonic series. But for example, if we know, so say we are comparing 1 over n to 1 over n squared. Oh, actually, that was a decent example. We produce limit as n goes to infinity of 1 over n. And we know this goes to 0. This is inconclusive because this we know is converging, but this we know is diverging. So this doesn't tell me that they have the same behavior. For them to have the same behavior, your comparison limit has to equal to some finite number.